All right, so the title of this module is Symbolic Integration and Differentiation, and let's jump right into the MATLAB code and discuss how you do this via MATLAB. So I usually like to start with a command called clear all, just to clear up the MATLAB database so that if there is any intersection between the variables, they can all be cleared up, and then you can reintroduce the new values of variables and so on and so forth. This is how you introduce the symbolic variables. So it goes by the command symbs, and my symbolic variable in this case is just x. So x is a symbolic variable. I'm going to show you how to take the definite integrals. It's done by the command int. If you need to know anything about MATLAB command that you haven't seen before, you just type up help and the name of the command, and it will give you everything you need to know. Okay, so you can read about this. What we are doing right now is we're doing the definite integral. So we are integrating the expression that is listed the first under the command int, and these are the limits of the integration. So I'm integrating this function that I just made up between -1 and 3. And MATLAB is supposed, if I run this file, MATLAB is supposed to give me the value of that integral, -2/5. Let's move on. You can take indefinite integrals and the only difference is that you don't specify the limits of integration. So you use the same command, but you only list the function and the variable of integration in this case. If there is no any doubt about what the variable of integration would be, then you don't have to even list this. As I point out here, you may choose not to specify the variable of integration. You just simply write int and the function that you want to integrate. If there's no any doubt about what the variable of integration, MATLAB will figure this out on its own. So I gave you two ways to write this down. The answer obviously should be the same. And you can see that you have the same answer for both functions. You can evaluate the integral function. So let's say you might not bother to know what the integral function looks like, but you can evaluate that function at a specified point. For this, you use the command subs. So you can evaluate, that's what I'm saying here, you can evaluate the value of the integral function at a given point. So let's evaluate the value of this integral at x equal 2. For this, we're going to implement the command called subs. Subs is basically a command that allows us to substitute for some symbolic variables with either other symbolic variables or the numbers, the actual values. So in this case, what we're doing is we're implementing subs. It's going to substitute in the expression that I call integral, and remember the integral is that indefinite integral that I have taken earlier. It's going to replace x with the value 2. This is how you evaluate a given function at a given point. Okay? So the outcome of this should be just a value. So if we run this file, the value is 1/5. Okay? Next, suppose you want to plot this function. So you have taken the integral, and again, let's say you don't bother knowing what that integral looks like. There might be a closed form expression, but let's say you don't care about that. How do you plot without knowing what the function looks like? This is a procedure. Okay, so I point out in every comment line, I point out what we do next. So plotting the obtained integral function versus x. For this, I'm going to define a vector of points on the x-axis. This is done through the command called linspace. If you read about that, again, you can type up help linspace in MATLAB command window, and it will tell you everything you need to know about it. One thing you need to know is that you specify the limits of the interval, and MATLAB will generate We'll split this interval into 100 equally spaced points between x1 and x2. So I'm creating a vector of equally spaced points on the interval between -10 and 10, because that's where I want to plot my function. So basically what x1 is, it's a vector of points between minus 10 and 10, equally spaced, and 100 of them. Okay. Then what I need to do is I need to put a correspondence between the points on that x-axis and the values of that integral function. And we can go back to the subs command that we just talked about and say subs in that integral function that we know, I'm going to replace x, which is a symbolic variable, with the vector x1. So what comes out of this, I call it integral 1. So integral 1 is an array of points which correspond to the values of that integral function evaluated at each point on the interval between minus 10 and 10, equally spaced. Okay, and then it's just a matter of plotting x1 versus integral 1, x versus y. Okay, so that's what it should look like. Why? I used to be able to do that. Oh, it's right here. Okay. Okay, so that's what the plot looks like. This is the plot of the function that represents the integral of the function that you have defined earlier, and I'm plotting this between minus 10 and 10. That's what it looks like. I want to show you an alternative way of plotting a function that's actually a very quick way of plotting if you know the closed form expression. So this is what I say here. If you know an explicit form of the function, you can use command fplot, and it will plot the function versus x. The syntax of this command looks like this, so you just have to be a little bit careful, or you would have to, again, type up help fplot to know the syntax so that MATLAB doesn't complain about the way you write things up. But the way to understand here is that at x means that you are plotting the function of x. This is the function itself, and I'm grabbing that function from the command window, which gave me the value of that integral function. So it's a closed form expression. I'm going to plot it between minus 10 and 10, and just for distinction, I'm going to add the color red. Okay, so I'm supposed to get now two plots. So one plot was for the previous way of plotting things, when I generated two arrays of data, so I plotted them one against another. And this one, the second one, the red one, is when I use the command fplot, when I use the closed form expression for the function. So as you can see, those are identical plots. It's just a couple of different ways to make up a plot. Integration with multiple variables. Okay, let me see. Okay, let's start with this. Let's say you have a function that is a function of two variables, and you want to take the integral with respect to one variable. That same command called int can handle this. You just need to specify what is your variable of integration. In this case, I specified to be x. So if I want to integrate the function exponential of x times z, two variables, but I want to take the integral with respect to x, this is how I specified, and MATLAB will integrate this, and eventually it will be the integral function eventually will be a function of x and z, but again the integration is taken with respect to x. You can do the similar thing by making z as your variable of integration. In that case, you would have to specify z after the comma here. Okay, so I'm going to run this file, and I'm going to show you both ways of obtaining this. So you can see that the first integral is when x was the variable of integration, and the second integral function is when the z was the variable of integration. And of course, each time you have two variables and you integrate with respect to one, then another one becomes sort of a constant. Okay? You can check this manually and verify that we did indeed get the correct answer. Plotting the graphs of the integrals for different values of the parameters. So in some of the assignments, you might be asked to do a certain routine repeatedly through the for loop. We covered the for loops extensively in other modules, so we're going to build up on that knowledge. But this is what it looks like. So I would like to integrate a function which is dependent on a parameter, and I want to plot it every time I generate the integral. So this is how it's done. So let's take a look at this piece of code. I am integrating a function sine of x times z. Okay, and z is my parameter. Z is not a variable, z is a parameter, and x is a variable. Parameter z, let's say, takes certain values. I'm going to define those values in this array. So I'm going to define z1. It's an array of values between 1 and 5 with the step 1. Again, you can manipulate this any way you want, so z1 is going to take values 1, 2, 3, 4, and 5. So 5 values in total. And for each value of z1, I would like to integrate the function sine of x times z and plot this integral function every time I assign the value for z. So this is how we do this. Make sure you open up another figure, otherwise MATLAB will superimpose the new plots onto the existing plots. So you want to separate those by defining a new figure. As before, since we're plotting between minus 10 and 10, I'm going to define the vector of x values between minus 10 and 10, but again, you can choose the interval yourself. It's done through the command linspace. So now x1 is the set of 100 points equally spaced between minus 10 and 10, and I just need to assign the values of the function for each of those points. I have to do this through the for loop because the value of the parameter z changes. So I'm going to let my internal for loop counter I run between 1 and the length of the vector z1. Since we counted the number of elements in the vector z1, that's 5, so I is going to run between 1 and 5. Each time I'm going to integrate the function sine of x times the current value of the parameter z. So that's why I'm saying sine of x times z1i. Okay? And the integration is going to be done through x. So x is my variable of integration. Once it's done, remember what we've done before in order to build up the array of y values, the vertical line values, I'm going to have to do the substitution. So I'm going to substitute in the expression integral 2, which is basically the integral of the sine of x times z, I'm going to replace x with x1, that array. So what comes out is, I call it integral 2. Again, integral 2 is the array of values of the integral function for each value of the for each value of x between minus 10 and 10, and there are 100 of them. And then now it's just a matter of plotting. Don't forget to put hold on, otherwise every time MATLAB runs the for loop, it will erase the existing plot and put a new plot on the figure. So you want to, if you want all plots to be present on the figure, you want to hold on, put the command hold on, and then plot what you want to plot. So I'm plotting x1, which is the array of x values, versus the array of y values, which I call integral 3. To distinguish them, you can play with colors. So I'm adding the option of colors. Now to explain this rent situation, if you go to Google, and let me show you very quickly. So colors in MATLAB. There's an explanation. So you can create colors using the RGB coding. So RGB coding represents 3 numbers that stand for a particular color. For example, 110 stands for yellow, 101 stands for magenta. So those numbers have to be between 0 and 1. In this code, I randomly select these numbers. So rand13 stands for 3 randomly selected values. And rand command is taking the values between 0 and 1. This is exactly what I want to generate the colors. So it will, each time the code is run, MATLAB will select the random selection of 3 numbers, which will correspond to a certain color. And that's how I create a colorful graph. So you will see that at the very last figure. There it is. So I have 5 graphs in total. They're distinguished by different colors, and that'll be it. In a very similar fashion, so this is integration. In a very similar fashion, let me show you how we do the differentiation. So I will just follow the same footsteps. The only difference is the command. For the integration, it's the int command. For the differentiation, it's diff command, D-I-F-F. Okay? So I will run through this rather quickly because everything is pretty much the same. So I define a derivative of a function through the command diff. Let's say I want to differentiate the function x squared times tangent of x. I'm going to differentiate it with respect to x, but you don't have to specify it. If there's only one variable, you don't have to specify which variable you're taking the derivative with respect to. So you can either do this or you can do this. Okay, and let me comment out everything else so that you're not confused for now. All right, so if you run this, MATLAB will take this symbolic derivative. Keep in mind that MATLAB doesn't know all the trigonometric identities, and you will see that, as a matter of fact, tangent squared of x plus 1 is actually 1 over cosine squared of x. So you can simplify it that way. MATLAB is understandably not aware of all trigonometric identities, so let's forgive MATLAB for that. But it doesn't prevent you from all the manipulations that you need to do with the derivatives. So you can evaluate, as before, you can evaluate this derivative in using the command subs. We've done that before. We're repeating the same thing here. So I'm evaluating the derivative function at pi over 4. So I'm using the subs command. So subs command in the expression called derivative is going to replace x by pi over 4. And it's going to give me the value. Alternative expression, so let me run this and then I'll explain you why I use another command. So if you use this directly, MATLAB will give you this answer. And MATLAB can actually calculate what that is through the command called eval. So if you want to know what exactly that is in terms of a rational number, you just use the command eval, and in brackets you use the formal definition of that value, which I call derival. So this and this are the same things. You just make MATLAB calculate it in terms of the numbers rather than the symbols, like pi. Plotting is the same routine as before. So you define the lin space. Here I want to plot the graph between minus pi over 3 and pi over 3. We want to avoid zeros, or I should say pi over 2, because cosine is equal to 0, so we want to avoid the singularities. So it's between pi over 3 and minus pi over 3 and pi over 3. In the same fashion, I'm replacing in the expression for the derivative, I'm expressing the symbol x with the array of points between minus pi over 3 and pi over 3, 100 of them, so that I can create the array of the value of the function. In this case, it's a derivative function. And then it's just a matter of plotting one versus another. So you do that. This is what it looks like. An alternative way, if you know the closed form expression for the derivative, there is an easy way to plot a function through the f-plot. So remember, the key difference between f-plot and plot is that plot uses the arrays of points on x-axis and y-axis. So for each point, it needs to find a corresponding value on the y-axis. Okay, but fplot makes it a lot easier for you if you have a closed form expression for the function. So this is the function I want to plot. I want to plot it versus x, specify the limits, and just for the fun, add the color if you want. You're supposed to get the same graph. Okay, so the graph looks like this. It's the same graph, it's just MATLAB, for some reason MATLAB uses the different scaling on the axis, but it's the identical graph compared to the previous one. Okay, next is differentiation with multiple variables. Okay, so again, you define the symbolic variables. In this case, that would be x and t. And you take the derivative through that same command, but you need to specify what is the variable of differentiation. So if it's x, in that case, then t will be viewed as a constant. So MATLAB will give you the answer for that. And if it's t that you're taking the derivative with respect to, then t would have to be specified under the command diff. Okay, so you get for each of those commands, you're going to get a different answer. So this is when x is a variable, and this is when t is a variable. Okay. Plotting the graphs of the derivatives for different values of the parameters. Again, this is more of a task, more of an example to show you how to repeat the same routine several times through the for loop. Just again, the refresher of the for loops. So let's say I would like to take the derivative of the function sine x times t squared. Okay, I want to take the derivative with respect to x, and I want to plot the graph of that function with respect to x for different values of the parameter t. Okay, for that I define the array of values for the parameter t. Make sure to use different symbol. So because t stands for the symbolic variable, so t1 is got to be something different. So t1 is the set of values of the parameter t that I want. So let's say from 1 to 5 with the step 1. So it's going to be 1, 2, 3, 4, 5. So 5 values of the parameter t. I'm going to define the same array or vector of points on the x-axis from minus 10 to 10. There's no singularity, so we don't have to worry about that in this particular function. Don't forget to open up a new figure. And then I'm opening up my for loop. So my internal for loop counter I is going to run from 1 to the length of the vector t1. That's going to be 5 in this case. Each time I'm going to take the derivative with respect to x with the current value of the parameter t. That's why I'm saying t1 sub I. Then I'm going to build an array of the functional values. For this, I'm going to use the subs command again, and I'm going to in the expression derivative for, which is this expression, the expression for the derivative itself, I'm going to replace a symbolic variable x with an array of points x1, 100 points. I'm going to get, as a result, I'm going to get the array of the values of the function. And then it's just a matter of plotting one versus another. Don't forget, hold on, otherwise at the end you're going to get the last plot only. You're not going to get all 5 of them. And then you can do the same thing with the colors. So if you run the file, this is what you get. Okay, so you get 5 plots in total on one figure. And that should end this module.